So let's begin. Let's start with the first problem. So you are given an array. So the input is an array of n integers, and this array is to be interpreted as the heights of a sequence of n buildings, let's say along a street, a one-dimensional street. Now there is an ocean on the right side of these buildings. So if we imagine this is our array with indices from 0 to n minus 1, we have to pretend that on the right side there lies the blue ocean, and each of these cells here has a building, and the number in the cell is the height of the building. And a building has an ocean view if the building can see the ocean without obstructions. So more formally, a building has an ocean view if all the buildings to its right have a smaller height. So what we want to do is to find out which buildings have an ocean view and return them as a list. Particularly, we want to return their indices in the array, or you can say their locations on the one-dimensional street, sorted in increasing order. That means we want the list of buildings to be returned in a left to right order, whatever buildings among these have an ocean view. So to take an example here, a toy example, if the heights are 4, 2, 3, and 1 along the street, that just means that, let's say this is the street, the first building has a height of 4. So let's say this is the height. Second building has a height of 3. The third building has a height of 2. And the first building has a height of 1. So if you notice, the building on the extreme right will always have an ocean view because there is nothing obstructing its vision on the right side. The building to its left also has an ocean view because you can climb up to the top floor, or I guess that's the top floor, from where you can see the ocean. The next building also has an ocean view from the top floor, and so does the first building. So all the buildings here have an ocean view. So what we need to return for this input, two. Well, I'm actually taking this second example here. So in this second example, where all the buildings are in reverse sorted order of heights, every building can see the ocean, and so we need to return 0, 1, 2, and 3, the 4 indices of the buildings that have an ocean view in a left to right order. The first example has 2 and 3 swapped. So if 2 and 3 were swapped, we would have a building of height 4, followed by a building of height 2, followed by a building of height 3, followed by a building of height 1. That's the sequence along the road. So this building has an ocean view. This building clearly has an ocean view. But this particular building is obstructed. So the view is obstructed because even from the top floor, you can't see the ocean, since there is a taller building on its right side. And finally, the leftmost building also has an ocean view. So which buildings have an ocean view? The building at index 0, the building at index 2, and the building at index 3. So what we are supposed to return here is 0, 2, and 3, the indices of those buildings. Third example, what if the heights were 1, 3, 2, and 4? So let's go through that. 1, 3, 2, and 4. So again, we can see that the tallest building, or the rightmost building here, will always have an ocean view. This one is obstructed. This one is also obstructed. And so is this one. So all 3 of these are obstructed. So only the building at index 3 has an ocean view. So what we return here is the result has only a single index, index 3. So the heights of the buildings are guaranteed to be positive, positive integers. So that's the description of the problem. And let's try and walk through our basic problem solving strategies and see where they lead us. So if we were to use a brute force approach, we would try to be exhaustive. That means we would look at each building and find out whether or not it has an ocean view. So from the problem description itself, we know that a building has an ocean view if all the buildings to its right have a smaller height. So for each um, building in the array, we check to see if all the values on the right side of it are smaller, and if so, then we add this building to our, or rather the index or the location of this building to our result list. Uh, Otherwise, we just ignore it and move on. So that would be the approach. So if we have, what would be the complexity of this approach? So for each building, let's say at a general building is at the ith index, we are going to scan all of these indices from n minus, from I plus 1 to n minus 1. So there will be roughly n minus I such indices. Uh, and or let me see, n minus 1 minus I plus 1 plus 1 to be exact. So that is n minus I minus 1. So we will look at roughly these many values. And in the worst case, um, how much time will this take? If we are scanning from left to right, as soon as we see a building with a taller height, we can say that the ith building is obstructed and move on to the next. But in the worst case, we will end up looking at all of those values. So for the leftmost building, we're going to end up looking at n minus 1 values. For the next building, we're going to end up looking at n minus 2 values, and so on. So in total, we're going to end up looking at these many values down to 0, I guess. So that's n times n minus 1 by 2, and so that's order n square. So that's where we are starting out. The brute force approach, that's quadratic time, and which doesn't require any auxiliary space. And our goal here is to improve on the brute force. We want to bring down this complexity from order n square to linear time. Okay, so the goal is to bring this down to linear time. And let's see if we can do that by next moving to decrease and conquer approach. So a decrease and conquer approach would normally begin by you pretending to be a lazy manager and deciding that instead of looking at all the buildings, you're just going to focus on one of them, let's say the leftmost building, and you're going to try to figure out whether the leftmost building has an ocean view or not. How do you do that? Well, you will look at all the buildings to its right. So there are n minus 1 values here. You look at all of them and verify whether or not that building is to be included in the result. If it is, then you add it, and then you pass the baton or the remaining subproblem of slightly smaller size to a subordinate. So that's all you do. Your subordinate does the same thing. He or she is equally lazy, and they will in turn hand over, they will just check whether the building at index 1 has an ocean view or not and add it to the result if so, and otherwise pass the baton to their subordinate. And so in this way, each manager is ending up doing work that is um, proportional to the number of buildings on the right side. So that is uh, in general going to be uh, proportion. So the root manager, for example, will have to do work that's proportional to n, or you can say n minus 1, but it doesn't matter since this is asymptotic analysis, and then hand over the remaining subproblem to a manager who is going to pick up this subproblem size n minus 1. Now this recurrence is the familiar recurrence. You've probably seen it many times with insertion sort, bubble sort, and so on. We know that this is quadratic time. In fact, the implementation that we write for this kind of work will essentially be the same code as we wrote for, or as the same code that we would write for brute force if we were to implement the brute force approach. So now our question, the question is, can we speed this up? Is there, so let's say I have done some work as the root manager. Is there something that my subordinate could use? Is there some information I could pass down to my subordinate which would allow my subordinate to speed up the determination of whether or not the next building has an ocean view? Well, I, as the root manager, would have looked at all the values at the beginning. So is there any value among them that I could maybe pass to my subordinate? Now you might think, well, the tallest building to my right could be something that I pass down to my subordinate. But if I pass on that information, which is the tallest building, it's possible that the tallest building could be the building to my immediate right. That is, it might as well, it could be my subordinate's building. So in that case, my subordinate would not be able to tell whether or not there is another building. Maybe there could be another building on the right side which also has the same height, right? There can't be a taller building, that is for sure, because if there was a taller building, then I as the root manager would pass the height of that building to my subordinate. But it's possible that another building of the same height might lie on the right side, and there is no way for me to figure out whether or not that's the case except by doing a linear scan. So just passing the maximum value down to my subordinate is not going to be sufficient for that reason. Now, so it looks like we're kind of stuck, but this is where we could go back and recall that there is directionality to this problem. So the ocean lies on one side, and we know that the building on the extreme right is guaranteed to have an ocean view. So normally decrease and conquer can be used in either direction, from the left end or from the right end. But in this case, because the ocean lies on one side, what would happen if we did decrease and conquer? So this is left to right. Let's try doing decrease and conquer from right to left and see if that makes a difference. So in right to left order, I as the lazy manager would focus only on the rightmost building. Now the rightmost building is guaranteed to have an ocean view. Maybe I'll add it to the result, and then I'm going to pass the remaining subproblem to my subordinate, who will again look at the rightmost building of his or her subproblem. And if this is implemented in a naive way, we will get exactly the same recurrence here. But now we want to ask, is there some information that a general subordinate, say this subordinate whose subproblem ends at index I, is there any information that this subordinate could get from his or her manager which would allow that subordinate to uh, avoid looking at all of these values on the right side. So each manager here is focused on the buildings on the right side of their extreme example. So now let's ask the same question. If we could um, get some information from our manager, namely which is the tallest building on my right side, that information could help us determine whether or not this building has an ocean view, right? So what do I need to tell whether or not this building has an ocean view? I just need the height of the tallest building on the right side. And since all my managers are looking at examples from the right side, I could inherit the maximum height from my immediate manager, and I could use it to tell whether or not my building has an ocean view. So that wouldn't require any work from my side, because if that maximum value is passed down to me in constant time, I would be able to tell uh, whether or not my building has an ocean view. And having done so, I could reduce the problem to a slightly smaller size. Now, this recurrence will lead to an improvement in complexity because we can just keep expanding it out like this. And so eventually we'll get a bunch of C's. Every manager spends a constant amount of time. We get a linear time solution this way. So it's an interesting example where naive decrease and conquer uh, seems to work, uh, but in only one direction. Only if we go in a right to left direction, not if we go from a left to right direction. So let's write the code for this. So let's think of what work an arbitrary manager is doing. A manager who's responsible for the prefix of the overall array ending at index I. What work is that manager doing? Well, that manager is going to inherit the maximum height. So let's say that's going to be passed down by their immediate manager to them in a variable. And so we will just look at, so what is this ith manager going to do? He will just look at what the see, what's the name of the array? Heights. If heights of I, if the height of my building happens to be less than or equal to the maximum height that I'm getting, that means my building is obstructed, right? My building that won't have an ocean view. So in that case, I don't have to do anything actually. So when do I add my building to the result? Well, only if my building has a height that is bigger than the maximum height. So let me change this, since I'm going to perform some action only if the height of my building is bigger than the maximum height passed down to me. This is where I will append my building, or you can say the index of my building. But conceptually, we are just appending our building to the final result. But in this particular problem, we are asked to append the location of that building. And so that's all I do. And then I hand the baton down to my subordinate, who is going to expect from me the same information that I got from my manager, namely the maximum height. Now it's possible that my building might be the tallest building so far, in which case the maximum height variable might get updated. So that work is something I need to do just to prepare the just to enable my subordinate to be able to solve their local problem, which is so this is going to be updated to the max of whatever the current value is, and potentially updated to the height of my building if my building happens to be taller. Right now, I could have just written this within the if condition, right? So otherwise, it's just going to be so I could do this, or I could just within the body of this if clause, I could reset max height or update max height to be equal to heights of I. And that's all I do. And every manager does the same thing. So I could take this piece of code and stick it inside an outer for loop. Sorry, now we are actually going in a right to left order. So we will start from n-1 and come down to index 0. And at the end, our resulting array, so our result array, let's say it starts out being empty, an empty array. It's a dynamically resizable array. So we keep stuffing building addresses into it wherever we see a building having an ocean view. And so at the end, we would have the result containing the indices of all the buildings. But because this is done in a right to left order, the values in the resulting array would have been accumulated in a right to left order. For example, the heights here were 4, 3, 2, and 1, and all the buildings had an ocean view. So in a right to left order, our result array would first have the 3 in it, then we would have inserted a 2, then we would have appended a 1, then we would have appended a 0. So the problem specification says that we need to return the indices sorted in increasing order. So that means in a left to right order. So what we need to do is to, before we return the result, we need to reverse it so that it's in a left to right order. So this reversal will also take order n time in the worst case because the maximum size of this result array is n. And so the total time complexity here has come down to linear, and we have still not used any auxiliary space. So we've kind of achieved what the problem was, what our goal was, to bring down the complexity from quadratic time to linear time. And so far, at least, we have not, we don't know what a monotonic stack is or why we need it. And we've solved this problem. One interesting property that we might notice is that when we look at which buildings have an ocean view, and we look at the order in which the buildings go into the result, it's not a coincidence that in a right to left order, all the buildings are going into the result in increasing order of height. So here, this building would go in first, then this would be the next building that goes in, and then finally this would be the next building. Right? So in a right to left order, the buildings are in increasing height. So that means if I was standing here on the beach and looking at the buildings, and if all of them were in a perfectly straight line, then I would kind of see the buildings one behind the other in increasing order of height. So the taller buildings would be behind and the shorter buildings would be in the front, or at least the sections of of the taller buildings I see would be behind. Here, the only building that's visible is this green one, right? So that's just an observation that I'm making about what goes into the result. The buildings with ocean view are finally, let's say after we reverse the result in strictly decreasing order of height. And that makes sense because if it was not strictly decreasing, uh, that means somewhere we would have a building with a particular height, and then to its right we have a building that's equal in height or taller than it. And that doesn't make sense because then this building would have been obstructed. It shouldn't be in the result. So strictly decreasing order is just something we are going to call as monotonically decreasing. So monotonically just means that it's always uh, decreasing. It's not even equal anywhere. So if you were to plot the height, well, this is a discrete scenario, but in general, when you have a continuous function and it's always going down, then we say it's monotonically decreasing. It will always have a negative slope. On the other hand, if we have a function that goes up or a function that is even flat, uh, we would say that it's not a monotonically decreasing function. Right? So the heights are strictly decreasing, and that's what we mean when we use the phrase monotonically decreasing. But we don't need any fancy data structure for this problem. We just have a simple right to left decrease and conquer getting us to the end. Okay, now let's see if there are any questions. Vineet?
Hi, Omkar.
Yeah.
Question is, we didn't consider the linear scan which would be required for the maximum height, right? Because
Uh,
I mean, in the line where we compare the height I with the max height, right?
right.
What if all the numbers what we get are in like say for instance if all the buildings except the last one are is the one which can see the ocean view, like all are in the ascending order.
Mhm.
So in that case, even if we keep adding the max values, we are adding that value into the data structure, right?
So something like this. All of them are in ascending
Ascend.
order.
So
From so left,
ascending
ascending from
from
left to
left,
right.
yeah, left to right.
Okay, so it's like this. Okay.
And we are supposed to move from left to right, right? From an arbitrary position of I towards n minus 1. Now, if we consider the ith, yeah,
So we actually are moving down from n minus 1 to 0. We are going in a right to left order, not in a left to right order.
okay, okay,
So, by the way, the max height, initially when we start out at the right end, um, this max height variable, since there's nothing on the right side of the rightmost building, there is no obstruction, so we can initialize it to 0.
okay, got it. Yeah, thanks.
Okay, any other um, questions on this? Gopal Krishnan?
Yeah, Omkar, can you please repeat that? What do we call monotonically?
So when you have a sequence of values, that sequence is monotonically decreasing if every value is that you see in sequence is smaller than the previous value. So the values are just going down continuously. They don't. They are never flat or they never increase anywhere. They're just strictly decreasing all the way from beginning to end. So the heights of these buildings are the heights of the buildings which go into the result
Hmm.
are going to be in strictly decreasing order. It's just a property that we are observing of the in the solution. So I've just made a note of it. We'll
Okay.
so because we're going to use it later.
Okay. Okay. Got it. Omkar, thanks.
And also you can visualize yourself standing at the edge of the
Yeah, yeah,
ocean
yeah.
and right. So you'll see the buildings. The buildings closest to you are going to be shorter. The buildings farther and farther from you are
Father,
going to
yeah.
be taller.
Dollar, yes.
Ashok.
Yes, Shankar, at the end, we are reversing. There is a reverse operation. What is its
Yeah, it
what is
just
it?
reversing an array.
Yeah, what is how what is its impact on time and space complexity? How?
So array reversal can be done in linear time because you know you can just swap the extreme elements, then swap the elements uh, at index one and n minus two, and so it doesn't need any extra space.
Oh, okay,
It can
okay,
be done in linear time.
okay,
So
fine. Yeah, thank you.
Biju,
Hey, Omkar. So this monotonic, is it only the decreasing or
it can
increasing
be
can
increasing
also
also. Yeah, if
increasing,
the
correct?
I mean so from right to left, the values are monotonically increasing in the result.
Okay,
From
okay.
left to right, the values are
Yeah,
monotonically
yeah,
decreasing in the result.
yeah.
Even if two buildings
Also,
have the same height, uh,
mhm.
they, the building on the left should not be in the result because it needs to be strictly taller than everything on its right in order to have an
Okay,
ocean view.
okay. Also, we can achieve this using recursively also, right? Instead of for loop.
Yeah, you can
The-
implement it recursively, but there's no advantage of using a recursive implementation for a decrease and conquer uh, algorithm, decrease and conquer an algorithm that's relying on this chain of managers doing the work in a top-down way with only one subordinate, right, per manager. So we can describe this work using a for loop
Mhm.
instead of, sorry, I have to reshare. We can describe this work in a for loop instead of implementing it recursively. So because in the recursive implementation, we would end up using space on the call stack.
Okay.
So why use a recursive implementation when you have a
Yeah.
much easier iterative implementation? So what I meant is whenever you have a decrease and conquer approach, either top down or bottom up, where the work is being done in a top down way in this particular problem, and it's an array, so uh, you can you can scan the array in a right to left order in a simple for loop. So whatever work each manager is doing, you just describe it as a block of code, and then you just
Okay.
embed it. You just embed it in an outer loop, and that should make the code run.
Yeah, yeah. Makes sense. Yeah. Thank you.
All right. So this part is here. Okay, Garrett.
Okay. So my question is, how do you know you have to go from right to left versus right. I guess in this question you can explain why.
Right.
So is this like a thing that we have to try if it's like a question we've not seen before? Like if left to right doesn't work, then maybe we try to do the same thing but from the reverse order. That's one of the challenges that I have in like figuring out which is the right way to look at things.
Yeah, normally it doesn't make a difference, but there are a few problems where something is changing in a very different way, or the situation is very different on one side than the other. So for example, another problem, for example, where a right to left order would help, I don't think I've done that in any floater, is there's a problem called next permutations, where you're given a permutation and you have to sort of generate the next permutation in sequential order. So there also, when you use a decrease and conquer approach, what you find is, to get to the next number. So think about how you do addition. Suppose I gave you a sequence of digits in an array and I asked you to like increment it by 1. Well, the digit on the right is guaranteed to change. Maybe the digit to its left might also change. Maybe the digit on the left would also change. But you see that the ripple effect when you do addition is in a right to left order. So it would therefore make sense to simulate addition again in a right to left order, because that's the order in which we actually execute the algorithm. So that's another example where right to left order would work. I mean, would be actually the way to go, not a left to right order.
Okay, got it. Thanks.
Yeah, this one is asymmetric in that the ocean is on one side, and so if information comes in from the same side as the ocean, then it's easier for me to use. Whereas if information is coming from the left side about what lies on the right, then I myself lie on the right side of my manager. So my own value is kind of subsumed within that information. So it's hard for me to subtract out my value. So whereas when we are going right to left, that maximum height is kind of getting updated and added to, right? It's hard for me to subtract my own height out, because I don't know how many buildings there were with that same height, just from the value that my manager passed. Hema?
Yeah, hi. I had a question where if there is more than one one building with the same height, then in this algorithm we would probably end up putting the index of the one on the rightmost side, and the answer. What would the answer expect? Would it expect the index on the left side instead, like
No.
from the?
Because the building on the left would not have an ocean view. It would be obstructed, since there is no place, there is no floor in that building which has an ocean view, since everything on its right side is blocked by this other building.
Okay. So that's why if they're equal, the max side we don't do anything. We just keep that index in the result. I see that. Okay.
Yeah.
Okay, understood. Thank you.
Asim?
Hi.
Hi.
Thank you for the explanation. I was trying to think, if and maybe you already discussed this, but if the height, if the height of the building were in descending order, right? Basically, which means the first building is the tallest, and then the first example, the 4, 3, 2, 1, in which your result is going to be, of course, it's going to be, of course, I'm just following the code. I was trying to do the stack trace of the code you wrote, right? So In that case, the max height was 0. The result is going to be the height I max of max height. So the very first value of the result is going to be the first building. But the second building, then the height is going to be 2. I mean, the second building will be, but the max height is going to be greater than the height, right? Basically. So the result is going to take, still the result is going to take the second building, but the height, but the max height will stay the same, right? Basically.
So if it's strictly decreasing, then the max height will keep increasing with each in each step, because if initially it's.
I'm saying if you have 0, 1, 2, 3, so your loop is starting from 0 or it is starting from the reverse side?
It's starting from 3 because we are going in a right to left order from 3 down to 0.
Oh, is it always going to be the case like that, or no?
No. For this problem, did you just join the class or were you?
I think I lost a few minutes in between, basically.
Okay. So yeah. So what I would recommend is, if you lose track of where we are, then just for making sure that others' time is not wasted,
Sure.
it would be good to view the recording. Maybe you can view the recording. I understand that different people might have other commitments, so please feel free to watch the recording, because we have a lot to cover and I don't want to.
I understand that. I was following, but then I lost this piece actually. Basically.
Sure. Yeah, this is in a right to left order, and it's only in some problems that directionality matters. This happens to be one such example.
I see.
Okay, so now I'm going to make a slight change to the problem condition, and it's similar to the switch that we made maybe in the sorting week. You might recall that there was a problem where we tried to find the kth largest or kth smallest element, and then we switch to a context where the numbers are coming in one at a time instead of being given together in one shot. So let's imagine. So this is a puzzle problem. So I can make up these constraints in the story of the puzzle. Let's imagine that these buildings are constructed in a left to right order. So maybe there's a complex with these apartment buildings, and the builder is building is doing the construction in a left to right order. So the array is not given to you in one shot. Let's say every day or maybe every month there will be a new building that's going to come up at the end. Now our task is to find which buildings have an unobstructed view, but not just once. We have to do this every single time that a new building comes up. So that was the context, if you remember. We made that switch even in the sorting week. So let me just call it as the streaming context. So the buildings are seen or constructed in a left to right order. You are expected to output the buildings with an ocean view. After every new construction. And now our goal is to minimize the total time. So we know that the algorithm we just went through takes linear time, linear in the number of buildings. So when there was only one building, we would spend a constant amount of time, let's say C, or let's say proportional to 1. Then when the second building is added, we could run the same right to left decrease and conquer algorithm. It would take time proportional to 2 and so on. So the values are coming in one at a time. And so when the nth building is built, we would end up taking time that's proportional to n minus 1, because we would look at all the preceding well, the algorithm that we had would actually proceed in a right to left order, and it would look at all the buildings in a right to left order. So it would take time actually proportional to n. So the total time across all of these updates would be therefore proportional to 1 plus 2 all the way up to n. So that's again quadratic. Okay, so across all updates. Now what we want to do is to actually ask, can we bring this down to linear time? So if we blindly used using our right to left algorithm, we would have to spend linear time, because the building that we constructed, or the latest building that was constructed, could impact the previous answer significantly, because a taller building that comes up is going to potentially block out some of the buildings that had an ocean view up to that point. I hope the context makes sense. The change in the context makes sense. So we want to ask whether the total time here could be brought down to order n. Now, with this constraint, we have no choice but to do a decrease and conquer, use a decrease and conquer strategy in a left to right direction. Because when the nth building comes in, an answer would have already been computed for the first n minus 1 buildings. And so we could solve the problem from scratch, but then we could ask, is there something we can do that will be a little faster? So let's ask this question. So instead of using this approach where we just execute the algorithm we had n times, can we update? So let's say when building I is constructed, or let's say that when the nth building is constructed, can we update the results from the first n minus 1 buildings faster, instead of recomputing the results from scratch? Instead of recomputation from scratch. So we are essentially going back and saying we are constrained to work in a left to right order. Now, it's a little different from the left to right order we saw earlier. Here we are assuming that if I am a lazy manager, I'm going to be called in to do some work only when the nth building is constructed. I don't want to be responsible for the entire work. I just want to take the responsibility for computing the result when the nth building is constructed. So that's the scope of my responsibility. Now somebody else under me is expected to have computed the result up to index n minus 2, right, for the first n minus 1 buildings. And they in turn would have done their work only after someone else would have computed the results for the first n minus 2 buildings, and so on. So we are talking about doing this work in a bottom-up way, right, and in a left-to-right order. If you look at the array, we want to do this computation in a left-to-right order. From the perspective of a lazy manager strategy using a decrease and conquer approach, we are assuming that the work would be done at the end instead of doing some work up front and passing it down to our subordinate. Does that make sense? That's the direction in which we are thinking. So therefore, I am going to focus only on speeding up things based on some information that is passed up to me by my subordinate, by my red subordinate. So the red subordinate would have given me some answer, right? Maybe this is the tentative result that was handed up to me, and the values here. So what do I mean by tentative result? I mean a list of buildings that have an ocean view among the n minus 1 buildings that exist up to that point. So my building it's as if it didn't even exist up to this point. So what's the tentative result up to that point? So the values here could be 20, 17, 15. They have to be monotonically decreasing. 8, 6, 5, maybe 4. Now my building comes into the picture at this stage, and I'm going to ask, how can I update the tentative result instead of recomputing from scratch? Now the addition of my building, the construction of my building is going to definitely cause it to become part of the result, right? My building has to have an ocean view because it is the rightmost building up to that point. Nothing else has been built beyond me. So it's guaranteed to be part of the result. But it's also possible that my building could obscure or obstruct some of the other buildings in the result. Now, since these values are, I'm going to write them as monotonically increasing here in a right to left order, monotonically decreasing in a left to right order. I'm going to the buildings that I'm going to obstruct are going to be some buildings at the right end of the tentative result, right? So because the shortest building is on the right extreme here, this is a little taller, this is a little taller, and so whatever buildings I obscure, they're all going to be bunched up here on the right side. So when I'm thinking about updating the results, I'm thinking about deleting them from the right side. And once a building is obstructed, it will permanently remain obstructed. It's never going to be part of the result. So I can dispose of some of these buildings. So for example, if the height of my building is, let's say it's 8, that means the buildings up to position 8, sorry, up to this value of 8, these 4 buildings have to be discarded from the result. And so the modified result is going to have 20, then 17, then 15, 14, and then my building, that's built, you know, the rightmost building. 8, 6, 5, and 4 would be deleted. So how do I want to do this? Conceptually, the update involves so the update involves an insertion, right? Insertion of my building into the result, and it also involves a bunch of deletions, and all these deletions are on the right end. And in fact, the building that's first going to be deleted is going to be the shortest building, right? That's the building with height 4. And in fact, this is the building that was added the most recently into the result. So the buildings are going to be, the buildings that are deleted are going to get deleted essentially in a last in, first out order. And if we want to perform these operations really fast, you can see that we would use a stack, right? So that to perform, so when is a stack used? A stack is used when we want to perform inserts and deletion with a particular behavior, last in, first out deletions in order one time each. Now, so that's what we are thinking of conceptually, to store the tentative result in the form of a stack so that the operations on this collection, which are all going to be performed on the right end, can be performed fast. In fact, even though it's a stack, we are going to, you know, not think of it in a very complicated way. This our tentative result can be imagined to be an array, a dynamically resizable array, which is growing and shrinking only from one end, from the right end. So we are really thinking of so the stack that we are talking about is implemented using an array. Under the hood, right? So that array is a dynamically resizable array. So like an array list in Java or a Python list. And the values in the stack, right, the values in our tentative result are going to be monotonically increasing from right to left, monotonically decreasing from left to right. Since the values monotonically increase or decrease depending on, you know, which direction you look at, we call it a monotonic stack. Okay, so conceptually it's a monotonic stack. In terms of implementation, it's going to be more, you know, simple, because we are just going to be adding and deleting values from the right end of a dynamically resizable array. So let's see what work is this manager going to be doing. An arbitrary manager who will be, let's say, looking at the ith building or the building at location I or index I. So so we know that the manager's own building is going to get added at the appended to the right end of the tentative result. But before we do that, we want to make sure that all the buildings that are now obstructed are removed. Right, so we will do something like this. We will say, as long as we see a building at the top of the stack. So by the way, when we talk about monotonic stack here, if this is our tentative result, this end is the top of the stack and the left end is the bottom. So the operations are performed here. The inserts and deletes are performed at the right end. So we can conceptually, if you want, we can invert it in a 90-degree with a 90-degree angle, and then we would be able to visualize this as a vertical stack. But so I hope the terminology here is clear. So each manager is going to take their newly constructed building and look at the top of the stack. If they see that the value in the top of the stack is less than or equal to their value, that means it's a building that is going to be completely obstructed, they would delete it. Right? In fact, I shouldn't even show this as added yet. So it's waiting to be added. First, we need to make sure that whatever buildings we see at the top, which are less than or equal to in their height than the height of my building, we want to eliminate them from the stack, and then only we add our building at the end. So in the worst case, maybe my building is the tallest building so far. Maybe in the worst case, everything gets deleted. That's also possible. So I'm going to do this with a while loop, since I don't know how many buildings are to be deleted. The deletion has to be done an unpredictable number of times. So as long as the stack is not empty, I'm just going to call the stack with a variable st. It's really a dynamically resizable array, right? It's the tentative result. As long as the stack is not empty and the element at the top of the stack is less than or equal to my value, we are going to delete it. We're going to pop the stack. We'll just throw out that building. Right, so we'll do a bunch of deletions here. And then at the end, what we will find is there will be a building here at the top whose height is bigger than mine. So at the end, what will happen is there will be some building whose height is bigger than my height. So maybe this is, we write some values here. Maybe this value, well, going back to that previous example, we delete 4, 5, 6, and 8, and then we'll see 14 at the top. So 14 would be here, and my building, which had a height of 8, would be then inserted. So I would push my own building into the stack at that point. So when I exit the while loop, let me write this in a comment. The element at the top of the stack, if there is one, there need not be, maybe the whole stack is empty, is the uh, is the, I'm going to write this as the previous larger value. Again, it's just an observation. It's the previous larger value in the original array. Right, so on each step, the values are going to be monotonically decreasing from left to right. And moreover, when it's time to add our building, it's going to be added right on top of the previous larger value in the array. Previous means lying on the left side, and the value on my left, which is larger than my value, is where I will be, forced to sit next to in the tentative result. And so if we do this, if every manager does this, if we do this in a left to right order from where the index I varies from 0 to n minus 1, we would have the result updated dynamically, and by the end we would have all the buildings in the right order, right? All the buildings with an ocean view in the right order, that is in a left to right order. And so we would be able to return, the stack itself as the result, because the stack itself is a dynamically resizable array under the hood. We don't need a separate result array. Now I'm going to make some changes to this, but conceptually I hope that's clear. This is not the final code, but before we write the final code though, we want to understand, does this really change the complexity? Like how can we say that we have done better than quadratic total time? So every building, so I'm going to argue that the total time taken is going to be linear. And it's not easy to see with a straightforward accounting, because whenever we add a new building, we are doing a variable number of deletions, and we know that in the worst case, maybe all the values before me got deleted. So the number of deletions that happen for a particular manager might be as big as order I if the manager is, the ith manager. But the claim is that collectively, when we amortize the total cost of insertions and deletions across all the managers, that is, if we try to compute the average work done by each manager by computing the total work and then dividing it by n, that average is going to end up being a constant amount of work done by each manager, which is why we're going to argue that the total work done has to be order n. So why is it that, how can we argue that each manager is on average doing constant amount of work? Well, we have to, just like we've done before for depth first search and breadth first search, there also we had a couple of loops, right? An outer for loop maybe, or and an inner while loop, or an outer while loop and an inner for loop. Instead of blindly multiplying the maximum number of times this can run and the number of times the outer loop is running, we want to get a tighter, smarter bound on the complexity. So let's focus on each building instead of focusing on what each manager is doing. If I am a building, there will be some work that will involve me. And so if I want to count how much work is done for me, let's look at the life cycle of a building. Each building is constructed at some point. At that point, we look at its value. And then it gets inserted into the array. Right? Insertion takes a constant amount of time. It might sit in the array and it may not ever be deleted. But it's possible that it might be deleted at some point. And when it's deleted, it's going to be taken out in constant time. So whenever a building is inserted, it's going to be inserted in a constant amount of time. Whenever it's deleted, it's going to be deleted in a constant amount of time. So that insertion deletion work is going to be constant. But there might be also, we might look at the value of the height of that building a number of times. So when we are in particular thinking of, when we are comparing the height of the manager's building with the top of the stack, there are two possibilities. Either that value gets deleted from the top or it stays there. So if it gets deleted, then we are going to consider that work as getting associated with the building that was deleted, right? So think of us as marking each building or attaching like a post-it note on each building, telling us how much work was done on it. When a building was added, that's when we write on the post-it note that a constant amount of work was done in inserting it. And then when we compare its value with each value at the top of the stack, that work we are going to tag to the building at the top of the stack. Right? The comparison, the work done in comparing is going to be added to the building at the top of the stack. Now, if the comparison was such that the top of the stack was not deleted, then we end up doing an insertion of my building. So that work, that final comparison and the insertion is what I'm going to associate with my building. But any comparison that results in a deletion, I'm going to tag the work to the building that was deleted. Right? So think about the total amount of work done on each building. So when it's added, there is some work associated with inserting it and some work associated with the last comparison of its height with the height of the building on the top of the stack. So that work is associated with the building that was inserted. Then later on, if I looked at its value, and looking at its value did not result in its deletion, that work is associated with the building that will be inserted on top of me. But if comparing the value did result in my deletion, that means there would be only one such comparison, because immediately after that comparison I would be deleted and nobody would ever look at me again. Right? So I'm giving an informal argument to establish that the amount of work done on each building is going to be a constant amount of work. And so across all the n buildings, we end up doing total of order n work. That's why this approach is the best one to use if we want to minimize the total work done in a so-called streaming context, or in a context where we have to not just solve the problem once, but we have to solve it for all the buildings one by one. Any questions about this analysis before we actually refine the code? Folks, it would be good to raise your hands if you have questions, because I'm not looking at the Q&A tab here. If you have questions, please just raise your hands. Balaji?
Omkar, sorry, I missed a few points when you were explaining it. Do you mind putting it in a pictorial way? Yeah.
Okay, so let me just write the accounting work. The accounting work that we are doing is so let's look at this. So when we look at the ith building, in left to right order, we compare its height with the height of the building on the top of the stack, right? We are comparing the height of my building with the height of the building on the top of the stack to see if the result needs to be modified, if the result built up so far needs to be modified. If the comparison ends up in deleting the element at the top of the stack, I'm going to assume that the work done in the comparison and in the deletion is going to get tagged to the building that was deleted. We compare it. We compare its height with the height of the building at the top of the stack.
Like incrementing +1 using a pair, something like that.
Okay, so you're asking what exactly do we put at the top of the stack?
Yeah, yeah.
Yeah. So for now, we are assuming that we have put the building. Now, obviously, what do we mean that we add the building? That the stack contains buildings. Well, there are two pieces of information we have about a building. One is, of course, its height,
Height.
and the other is, of course, its location on the street, right, which is given by the index in the array. So for our purposes, let's assume both of them are added to the stack, right? So when we look at the top of the stack, we see these two numbers for a building. What is its, and we may not need both numbers, right? I'm just saying if we want to just put everything on top of the stack, there would be only these two numbers, the height of the building and its location in the array. So in the original array. So we compare the height of the new building with the height of the building at the top of the stack. If the comparison results in deleting the building at the top, associate the work done with the deleted building. Right? Otherwise, we know that the height of my building is actually less than the height of the building at the top of the stack. Right? It's my previous larger value in the array. Right? So I'm not going to delete it because I'm not obstructing it. It's taller than me. Otherwise, insert or rather I should say associate the work done, and what work is done, that comparison operation plus insertion with my building or the ith building, right? It's the same thing. So we are accounting for the total work done in a more intelligent way by associating or tagging each elementary operation here with a specific building, and we are saying that comparisons that resulted in the top of the stack being popped, all that work is associated with the buildings that were popped. And finally, the last comparison, which resulted in the insertion of the the new building, the latest building, that work is associated with the latest building. So with this, if we do the accounting in this way, the total work, the claim is that the total work tagged to each building is constant. It's a constant amount of work. That's the claim. Why? Because each building is inserted once, right? What is the total work? The first time we see a building, the only work that is tagged to it is the work of insertion and a single comparison. I should say, plus the work done, the final comparison with the previous larger value, right? Or the building that's going to lie immediately on my left in the updated result. So that is constant. And the other work that is tagged to my building, if at all it is deleted, is the work of deletion plus comparison, with plus the comparison that resulted in my being kicked out. And so a single comparison, single insertion, single comparison, single deletion. These are the four, at most, these are the four pieces of work that would be tagged to each building. And so each building would be tagged with a constant amount of work. So across all the n buildings, the total amount of work done would have been order n. So this is actually a more sophisticated kind of analysis, or amortized analysis. So the work done with a single manager associated, if we try to quantify the work done by a single manager, it might be as high as order I or order n for the last manager, right? But that doesn't mean that across all the n managers the total work done was quadratic, because if the last manager had to do a lot of work, then the previous managers would have done less work because they didn't delete anything, right? They just saw the top of the stack and they saw that their building is not obstructing anything, and so the stack kept growing, which is why the final manager had so many deletions to do. So when we compute the average work done across all the managers, that would be constant.
Yeah, so assuming it is only either monotonically increasing or decreasing, right? It can't be all the way decreasing and the last value cannot be the tallest building. I mean, the rightmost one.
Yeah, so we are talking about specifically this scenario where the values in the stack are monotonically increasing or decreasing. So
increasing
when you look at it from left to right or from bottom to top, the values are decreasing.
Right. So assuming that the n minus 1 at the n minus when I is equals to n minus 1, n minus 2 is the only comparison that might be required, right?
When I is n minus 1, there might be n minus 2 comparisons that will be required because maybe all of them get deleted, right? But each of those comparisons is getting tagged with the buildings that are being deleted one by one. So the work done on each of these comparisons is getting distributed across all the buildings that were deleted. So each building gets only a constant amount of work tagged to it.
Okay.
Right. So in other words, the energy expended in running this algorithm is getting tagged to, each building, and we are claiming that each building is being tagged with only a constant amount of energy. So that's the logic behind this kind of analysis.
Okay.
So,
sure.
Yeah. Any other questions about the analysis? Jyoti?
Hello.
Yeah.
Yeah. So I understand the insertion thing. I'm able to understand that it will be a constant work. But in case of deletion, when we do the comparison with other values that are already in the stack, in that case, we are touching the other buildings, right? So
Yes.
how will that be a constant? Because if I am deleting next or previously five, suppose for five elements I'm deleting, then in that case, every element which was touched before, I'm touching that again. So it won't be a constant, right?
So let's look at this example, right? Suppose we are looking at this building with a height of 8, and we know that these 4 buildings are going to get deleted, right?
Yes.
So the comparison between this 4 and this 8, the work done in that comparison is going to get associated with this building. and this building is kicked out from the result.
Correct.
The comparison then between 8 and 5, we are assuming that the work done there is getting tagged to this building, and this building is also deleted after that. Similarly, the comparison between 6 and 8, the work done there is getting tagged to building 6, so the building with the height 6, it gets deleted. Same thing between these two buildings, the work done is getting tagged to this building, which is deleted. Now, when we compare 8 and 14, we realize that 14 is actually taller. And so we are going to end up inserting the 8 right next to it like this. So the final comparison here between 14 and 8, which was accompanied by a deletion, by an insertion, is getting tagged to the 8 or to the building with the height 8. So what's happening is every comparison is either followed by an insertion or a deletion. Right?
I understood that point. Every comparison is with insertion or deletion. But when you are at the ith index, in this case, you are at the 8th index, the last one. You are comparing it with 4, then with 5, then with 6, and then with 8. In that case, we are comparing and deleting at the ith index. We are doing it for the 4 times here, and at the 5th iteration, we are actually inserting. So how come that is considered as a constant? That's what my question is. In a single iteration, for like in the ith iteration, in this case 8, we are touching all the previous.
Right. So in the ith iteration or for the ith manager, the total work done is not constant.
Constant, right?
Yeah, it's not constant, but the total work done across all the managers is linear. It's linear because each building is tagged with a constant amount of work. And so on average, when we take that linear work and we distribute it across all the managers to compute the average, each manager ends up doing an average of constant amount of work.
Okay.
Yeah.
In that case, yes. Okay. In that case, yes.
Right.
Yes.
So each comparison is coupled with an insertion or a deletion. If it's coupled with an insertion, we are attributing the cost of that comparison to the element being inserted. If it's coupled with a deletion, then we are attributing the cost of that comparison with the element being deleted. And since each element is inserted once and deleted at most once, the comparison operations tagged to each element or each building can be at most 2. So the total work done or total work tagged to each building in this accounting scheme, right? It's not like we are saying the total work that's tagged to each building in the way we have accounted for the work is constant. And so across all the buildings, the total work done is order n. And so that makes the whole algorithm run in time that we say is order n.
Okay, this makes sense. Thank you.
So I'm going to, before I take more questions, I'm just going to refine the code here, and then I can take more questions. So firstly, this problem asked us to return the indices of the buildings with an ocean view in a left to right order. So let's see, what exactly should we insert into the stack? When we say the stack is not empty, and when we compare our building with the element at the top of the stack, might result in a deletion, or it might result in the insertion of my building. But what I'm supposed to actually append to the answer is the index of my building, not the height of my building. Right? But when I compare my height with the value at the top of the stack, I'm actually assuming that in the stack we have the height present because we are doing a height comparison. So in the stack we are assuming there to be heights, but what we will actually end up doing is for the surviving buildings in the stack, we want to have the indices at the end returned. So that means it makes sense to store in the stack both the heights and the indices, so that whatever the stack looks like at the end, we will just, take the indices in it and return those. Because if you just look at values, if there are just a bunch of values in the stack, that it doesn't tell us where those buildings were located, because there can be multiple buildings with the same height. So we are assuming that specifically that here the top of the stack is really a pair. So we are storing the height of the building as the first component of the pair and its location or index as the second component. So when we do st.top, we are going to get this pair. When we look at the top of the stack, we are essentially looking at a pair, but we are interested specifically in comparing the height. So we can just focus on the left component. Right, so the stack element is really a pair, right? A pair of, you can say, ints, pair of integers. The first integer is the height, second integer is the index. So we have the height being used in the comparison here, and so when we push here, when we push the when we insert a building at the end, we will insert the entire, not just the height, but also its location into the stack. Okay, and so at the end, our stack really is a stack of buildings, monotonically decreasing order of height from left to right, but these are pairs. What we really want is to return an array of indices. So we need to compare, we need to convert, or we need to transform the stack into a value, a sequence of index values. So we won't return the stack itself. We will need to so let's say our answer is just going to be an array of ints. So we will have to go through each element of the stack. For each height, comma, index in the stack, we're going to append or push just the index part into the result, and we return the result. Right, so this might take an extra order n time, just because the stack in the worst case might be filled with most of the buildings, just because they might be in decreasing order of height to begin with. So the total time, therefore, is going to be order n. So in some sense, we are using auxiliary space here, which is the space used by the monotonic stack, which in the worst case could grow to order n. The stack initially starts out being empty, an empty array. So I think this completes the code in a left to right order. Okay, Mohammed. Question?
Yeah, can you hear me?
Yes.
Oh yeah, I meant we could also avoid the pair, right? Like, so if we store only the indices, then we can just change the comparison to like while stack top the heights square bracket indexed on the stack top.
Sorry, I didn't follow you. You're saying in the stack, we just store.
Yeah, if you could just store the indices and then change
But
the
then
comparison in the while loop.
Oh, okay. You just store the indices, but then okay. So you will just look up the height by going to the array.
Index, we could
yeah.
avoid that pair.
Yeah,
Just a short optimization. Yeah.
Sure,
That's
you
it.
can avoid the pair. So conceptually, I'm writing it like this because conceptually, what we're doing is kind of throwing the building into the stack.
Yeah.
Right. And what is a building here? It's basically we just have two pieces of information about a building. So I'm just assuming that we store both pieces here. But yes, you can optimize it and store only the index. That's true. Manish?
Actually, the previous problem we solved, and that was without stack, and this problem we solved with the stack. So, what's the difference? So, if we take one problem, then we solve with these two approaches. The answer should be same, right?
So the answer will be the same, but the time taken. In fact, the time taken is also the same, but this monotonic stack approach ended up using extra space, right? It's using order n space. So in that sense, it's a little worse than the original right to left algorithm we had, the decrease and conquer algorithm we had. But we were assuming that we have to do this only once, right? Just like quick select in your sorting, quick select, if you have to find the kth largest element only once, then you have the quick select approach is the best. But if you had to keep the information updated each time for the kth largest element, every time a new element comes in, you have to update it and then spit it out. You can't do quick select each time because that would take order n times whatever the number of elements. So it would end up being quadratic. So we use the heap based approach. Similarly here, we are saying with the use of a monotonic stack, the total amount of work done, assuming that we have to do this work each time, would end up being minimized in this way.
So this approach we should use when we get those building heights as a string. So in that case, we should use this approach, right? Otherwise, the previous one, decrease and conquer from the right hand side should be the best one because we will not be using the extra space over there.
Right. So now obviously it's silly to think of this as a streaming context because the story in the puzzle doesn't make sense. But essentially, whenever the answer needs to be computed for each element, right, separately. That's what happens in the streaming context. Every time a new number comes in, we have to, do this. So, but it might not be given to you as in a streaming context. You might be asked, and you will see this in the next problem. You might be asked to compute the answer for every element. It's some kind of answer for every element, and in that case, we would. It would be expensive to do the right to left approach n times.
Yeah. Thanks.
Yeah, related to the previous discussion we were having just now, it's not easy to visualize how I fully get it. When the building is coming up every month, and we don't want to use the first method, right? We want to build on whatever we calculated when the previous building was added last month.
Right.
So, but what could be and given that we are using computer an algorithm to solve this, what could be the real life example where we can see the impact of using this more efficient algorithm in a streaming context. I'm not able to visualize. I mean, buildings are coming up. That's not the.
Yeah, I mean, frankly, this monotonic stack is really not a topic in even in a university algorithms course. It seems like a very peculiar thing to
Is it?
some of these interview problems.
Yeah. Okay. That
Because
was
it's
my
easy
question.
to it's very easy to implement, and so that's probably why it's just like segment trees and binary index trees. Something that can be implemented fast is what uh, tends to get asked. So
Okay. It is
maybe.
purely
Hmm.
theoretical, more theoretical thing.
Yeah, I mean, seems like it. Although if you so we have a monotonic stack. In a similar way, we could also talk about a monotonic queue, or you can say double-ended queue. We've seen some problems before where I think in the sliding windows classes where we had to keep the numbers in uh, like monotonically increasing or decreasing order, but it was a queue there rather than a stack, right? A double-ended queue. So there the problem, one of the problems there was, for example, finding the sliding window minimum or maximum, something like that. Was that one of the problems? I'm trying to. Raghu, do you remember which problem it was in the arrays series? Okay, Raghu's not here. Um, I think there were a couple of problems there. I seem to vaguely remember there was another problem also, which there were two problems there. Now, sliding window problems, you can say uh, maybe in a streaming context you have only a finite window to look at, and so if you want to just find the maximum or the minimum in a sliding window, then you can perhaps think of applications where you want to find, for example, the maximum temperature, let's say in a particular window, and that window keeps sliding as streaming data comes in. So to update it, you would use something like this. Have you seen the um, that particular class where I think we covered sliding window maximum or minimum? I forget which one it was.
Uh, are these part of extra videos?
Yeah, in the array floater series, there are I think about 10 or 11 classes I've taken so far. There are three
Okay.
classes on sliding windows, and I think in one of them there was this I think it's a hard problem called sliding window maximum or minimum, and so to keep that window updated with the minimum value, because every time a new value comes in, maybe an old value has to be kicked out. So how do you update the maximum or the minimum in that window?
Okay.
So
No, I haven't. Yeah, I know. I know. There is a question once. I have seen the question in one of the domain specific, not domain, this algorithm specific technical coaching session. I haven't seen the video. Okay, I'll see that.
yeah,
Thank you.
so, sure. Okay, so that completes our discussion of this first problem.